Okay, welcome to your first video lecture in Chapter 6 on Section 6.1, the definition of the Laplace transform. So many practical engineering problems involve mechanical or electrical systems acted on by discontinuous or impulsive forcing terms. In this particular case, the methods of Chapter 3, which were only applicable for nice functions, say from Calc 1 or 2, as forcing terms, this means that these methods from Chapter 3 are going to be awkward to use, and we're going to avoid those methods in Chapter 6. And so one way to address discontinuities is to use integrals. As we learned in Calc 2, integrals have a way of sort of smoothing out discontinuities in functions. And so what we're going to do is use an integral to transform our problem into a different problem. And the integral transform that we will focus on in this course is the Laplace transform. Okay, so the Laplace transform works by taking the initial value problem that we're concerned with, applying an integral transform, and giving us an algebraic equation, okay, involving a function big Y of s, where the independent variable here is a complex frequency, as opposed to in this left circle here, the independent variable is t, which is a time. Okay, so what we're going to do is take a Laplace transform, take a differential equation, which is hard, turn it into an algebraic equation, which is easy, and then transform back using what's called the inverse Laplace transform. Okay, so the Laplace transform involves an integral from t is equal to 0 to t is equal to infinity, and thus we need to review improper integrals from Calc 2. An improper integral over an unbounded interval is defined as the limit of proper integrals over finite intervals. So here we'll have this proper definite integral, the integral from little a to big A of f of t dt. If we push the upper limit big A to infinity, we have this improper integral there. From little a to infinity of f of t dt. If the limit exists, then we say that the improper integral converges. If the limit doesn't exist, which is certainly possible, we say it diverges. The type of functions that we will be considering in this chapter may not be continuous, as we said before. However, many of these functions may be piecewise continuous, and those will be the ones that we're going to consider. A function is piecewise continuous on an interval alpha beta if you can partition alpha and beta into finitely many subintervals. Okay, so subintervals, where the function is continuous on that subinterval, and then at those breaking points, or those partition points, f is finite left and right hand limits of the function there. So, for example, this is a function that is piecewise continuous, whereas something like if we had t here and we say had a vertical asymptote at a particular point, this would not be piecewise continuous because these limits would not be finite at one of the partition points. Okay, so we certainly need the only type of discontinuities to be jumps. Okay, so now we're getting ready to define the Laplace transform, which is a type of integral transform. An integral transform of a function f is an equation or a relation of this form here, where we take a function f of t, we pass it through via multiplication by a kernel k, which is a function both of t and s. We integrate away the variable t to give us a function of s. Okay? We call big F the transform of little f, and again, big F is a function of a different independent variable than little f. And there are several integral transforms that are useful in applied mathematics. For example, some of you in physics have seen the Fourier transform. In this class, we will concern ourselves with the Laplace transform, where the kernel in this particular case, k of st, is given by e to the minus st. Okay, and so thus the Laplace transform of f is the integral from 0 to infinity of e to the minus st f of t dt. Okay, so the interval alpha beta there is 0 to infinity. And so one of the main concerns is to determine when a function has a Laplace transform. So suppose that f is piecewise continuous on the interval 0 to big A for any a, so any sort of positive interval there, f will be piecewise continuous over that interval, and then f is bounded above by some exponential function with coefficient a whenever t is large enough. Okay, so f doesn't need to be small, it just needs to be bounded from above by some exponential function. If this is the case, then the Laplace transform, defined as we said in the previous slide, the integral from 0 to infinity of e to the minus s times f of t dt exists for all s greater than or equal to that a that we saw up there. And so in this chapter, we will deal almost exclusively with functions that satisfy the hypotheses, so functions that have Laplace transforms. So functions that are at least piecewise continuous and of exponential order with exponent a. And so when we say exponential order, we mean that f in absolute value is less than or equal to some constant times an exponential function with exponent equal to at. And to close this particular lecture, one thing that we can show that's relatively useful here is that the Laplace transform is a linear operator. In other words, if you take the Laplace transform of a linear combination of two functions, it's the linear combination of the Laplace transforms. So that's very useful, and that will help us tremendously in solving linear second-order differential equations with constant coefficients. Okay, thank you.